First of all, what do you ask to a storage system, okay? And I told you already that first things that we are working on is lower dollar per gigabyte. You want to spend less money for your storage. You want to store more and spend less, which is, you know, I can understand that, okay? Then we started thinking about that it's not longer, you know, it's not enough, right? So you could have more value from the data that you're saving, okay? Not just saving money, but you know, producing money from what you are saving. And what is serverless computing? So serverless is a cloud computing model for which server management and all the other components are delegated to the system, and you just don't know what's behind the scene. Okay, so everything is hidden from you. You just put the code. So in a traditional computing model, you have the application, you have the orchestration layer, you have the operating system, the hypervisor, or the containers, or whatever, and the data storage. It's really, really complex. Okay, so when you write an application, you have to understand all these pieces, or how they work, how they integrate with each other, and so on. With our model, it's much easier. Okay, so it's not just you have your application, you write your application, and the application is triggered by an event that is generated inside the storage system, and that's it. Okay, it's much easier, much easier to develop the application. But why? Okay, so first of all, you can offload tasks to the storage. So everything we intercept, like for example, I write something in the storage, and I want to do a task. I want to validate the data I am storing. I want to encrypt the data. I want to transcode a video. I want to whatever. Okay. Instead of having an external process, an external computing power, I can do it into the storage system. Okay. Think about, I put an image, I want to resize it, just to be sure that all the images are the same size. It's easy to simplify with this mechanism a lot of workloads for the same reason. Okay, so think about most of the streaming companies. They have several versions of the same file. Okay, so the new TV series, they don't have just one version. They stream a different version for each single device. So they detect the device that is requesting the video, and they send the right file, the right bit rate. If they detect that you don't have enough bandwidth, okay. So for the latest movie, they have 20 different versions, maybe more, and they have to transcode all of them. With this system, you just put the highest resolution in the system, and the system creates 20 versions. And that's metadata, and that's all the information needed to stream this video. It's just a simple operation. So you save the file, you don't do anything else. On the background, you started to create all the videos that you need. This is just a simple operation, so it simplifies everything. And as I told you, it's event-driven. So we detect an event, and we start the application. But actually, we already developed a second part that it's more time-driven. Okay, so every time in the night, like a cron tab job. Okay, every time you want, you can run on all your data, on a subset of data, some operations, and it's for everyone. So we support many languages and scripting languages. The idea is that even if you are a developer or a sysadmin, you can write a few lines of code to do what you need. Okay. Use cases. I mentioned very quickly transcoding, but you can do, for example, log analytics. Okay. When I save a log in the object storage, I can go through it and check for errors or whatever and raise an alarm. I can look into my Word files if I'm storing credit card numbers. I can check the validity if a PDF is a valid file. I can check whatever. I can do whatever I want, okay, because I have control of the data, of the metadata, and the events that is created. So it's just to, I have many hooks where I can I can operate on many different things, okay? And how? And this is Julien, yes, it's yours.
So I'm Julien, so I'm responsible of the Grid for Apps development, and I will present you how it works and what we are doing to make it happen. So a few topics I want to address. First, the concept that we deal with the Grid for Apps API, and the architecture of the solution. A bit about how we interact with the API, and a quick roadmap about what's coming next. So, about the node and about the task. So, we basically have bunch of nodes running the storage, and some of these nodes have usually a lot of CPUs, a lot of RAM that we don't really use when we run only the storage part. And the idea is you want to use this RAM and this CPU to run your task. So what we do is we install our runtime, our Grid for Apps runtime on it, and it's then able to run the user task. So it's not only what we design as task, is what you really want to do, so your code, and running on the same platform, on the same nodes. So nodes can be physical machines or VMs, so it's pretty much the same as OpenIO software for the storage. You choose, and for the task, they run as Docker containers. So if you already have some applications running on Docker, you can pretty much from today run it inside the grid. It's really easy to integrate. So the idea is, as the serverless computing model defines it, is you should not be aware of the complexity of the topology of the network, of the hardware running behind the cluster. You just want to interact with an API and run what you want. So users, they just speak to the API, they don't touch anything else. All the rest is handled by the system. So about the architecture, how we do it. So it's nothing very completely crazy here. So you have two parts, control plane, sorry. This is a part that makes the brain of the system, pretty much. You have the API that you connect to when you want to do your operations. And then you have the runtime running on the nodes. And the runtime is talking to the Docker daemon on each machines, on each nodes. The runtime actually runs the workload you define, and the control plane makes it happen in an intelligent way. So it repairs what's broken and schedule the task and so on. So the control plane. So we expose the grid API, so it's HTTP API. So it's create, update, list, remove kind of API. You manage some resources that I'm gonna talk about a bit later. And then you have the controllers, and the controllers are basically background tasks that makes the system intelligent. But the agent, so agent is a daemon you run on each node. they must have access to the Docker API. So they usually run as root. But the thing is, they fetch all the data and what you should run from the API, and they mix it in sync with what's actually in the Docker containers. So the API, so it's HTTP API, so you can access it with curl. So nothing very fancy requirements. So you can script, you can use any language you want to access it or modify it. It's resource-based, so it's really easy to understand how to manipulate the system. And so about the resources, so the thing is we have several basic resources in the API, and all these resources, they describe a certain state. So, for example, you describe the name of the container and what image you want to run from your container. This is a desired state for your cluster. These are just the specs, and they only represent what you want to run. And then there's the other part, which is the status. And the status is what's actually running inside your cluster. So what the system really achieved. And the role of the system is always to match, as long as it's possible, the spec and the status. So it's always trying to make it happen. So for example, if you say your spec needs to run 10 tasks and you only have 5 running, what the system will do is spawn 5 new tasks. Or if you have more of them, they will kill a bunch of them to make it even with the spec. So as an example of this, we have a resource in the grid, in the API, called a job. So a job is distributed workload. It can be something as a batch computation. So for example, let's transcode these millions of videos inside the storage. And the spec will, for example, define how many tasks you want to run inside the cluster, depending on the kind of performance you are expecting. The system will follow the job spec and start and the configure number of tasks. So the job status is constantly updated by the runtime. So the daemon running inside the nodes, they will check the status of the Docker containers and then check the spec and make sure everything is in sync. For example, if one task will fail, for example, the node is down or network error or something like this, the system will detect it at some point and start a new one. So you have self-healing kind of features, and you don't really care about once you created your job, you don't really care how it's going to be run. The system makes the best effort to run it. And then there's the most basic resource you can create inside the API, which is a task. And the task is a container inside Docker. So if you already use Docker now to run your applications, this is very easy to map, and this is usually the task you will want to create. But we provide some higher level resources that will create the task for you. So automatically we create the task, and you will mostly interact with higher level resources, such as the job. So as a task example, this is how it looks like in a YAML kind of representation. So of the resource kind. some metadata, so which namespace you want to run your task, and your name of the task. If you want to retrieve it later, it's easier to have a personalized name rather than just an ID. And then you have the spec, and the spec will here run a slip of 3000 inside a BusyBox image. So let's discuss an example of a job running inside a cluster. So I have a picture here, 2 nodes, and I want to process 3 files. So one way to do it, of the parallel processing, I will create 3 jobs, and each jobs will create 1 task. So I have in total 3 tasks, and each task will process 1 input file. Since I have only 2 nodes, I cannot run perfectly parallel, but I will run 2 tasks in the node 2 here. So this is a very basic approach, and it can work as long as you don't have that many inputs at the same time. Because if you remember correctly, the task is a Docker container. So imagine I have 1 million input files, you probably don't want to spin up 1 million Docker containers in your cluster. So there's a different way to handle this case, and is reuse the Docker container and the task. So you use parallel processing with a work queue, and which is what we do when we plug with the object storage of OpenIO. So we have work queues inside OpenIO, and they can catch the events of the storage. So for example, new content has been created or has been updated. Your task will be able to fetch the object and then process it and reuse the Docker container instance, which is much more efficient. So this is very easy to run highly distributed workloads. Just define that simple YAML file that I described, and that's it. I mean, there's not really advanced knowledge of how it's done behind the scenes. You just define a simple file. So about the roadmap of the current system, the software. So today you can run tasks with the API, and you have an easy-to-deploy test environment, which is just a single binary with everything on it, and you run your own cluster. And the beta will be available in October. You will have automatic scheduling, the ability to view the task logs directly through the API, and being able to create more advanced jobs. And yeah, I mean, that's it. So if you guys have any questions, we're gonna have an after lunch demonstration of the software and a use case about TensorFlow, which will run the combined grid for apps and the object storage of OpenIO to run advanced workloads using image recognition systems. So thank you very much.
So this concludes the morning sessions. Okay, we are very so we want to know from you later today, after this, the demonstration, what do you think about Grid for Apps? Because for us is something really new, and it's a huge differentiator compared to other storage platforms. Okay, we are no longer just a storage platform; we are a data platform. So please give us any sort of feedback during the day about this technology. Also to, Julien and the other developers will be available for talking with you about potential use cases, about how you can take advantage of this technology and so on. Okay?